Okay, let's come to bending issues. Okay, first one, let's talk about pure bending. Pure bending means what? We have only a pair of bending moments. We do not have any other force application. So this is a pure bending case. Okay, here I set up a coordinate system, and diameter again, it is d or phi. Okay, we may use d in analysis. And here a particular marker point, the red point for our attention. And I name the bending moment mz, or just simply m. Okay, so in this segment, in any cross section, we should say the same stress. Okay, and because we only have a pair of moment, so every cross section has to give out the same thing. All right, so then we can do any cross section. For me, I just want to do this one across the red point I just marked. All right, so this is a cross section. And because of this bending, we know the top is compression, bottom is in tension. So this is the bending stress distribution. We know that already. The middle line, it is the neutral axis. Okay. All right, so when we did this kind of stress distribution, we consider several conditions. First of all, the surface. Okay, the surface has to be stress-free. So the stress is in the surface, not on the surface. Second is that integration of the lower moment created by those stresses would equal to the bending moment itself. And the other thing is that the entire force, summation of all the entire stresses, we come out to a zero force, because in each cross section we only see bending moment, there's no force. All right, so at any location of y, okay, we measure y starting from the neutral axis, okay, at this distance, and then the stress can be defined by bending moment, okay, and multiplied by this y, and then divided by I. And I is called second moment of area, which we know that I equals pi d power 4, then 64. All right, it's called second moment of area. All right. Okay. Maximum appears in the surface. That's what we know, in the surface. Okay, when this y equals the radius of the shaft. All right, which red dot is the point, particularly for this case. All right, so the red dot is the bottom, that is under tension. The top is under compression, just opposite in signs. Okay, so we can write it down because the stress is along the x direction, so we can use sigma x. So when y equals d divided by 2, okay, bring this into that equation, definitely we get this one. Okay, and sometimes people call this, because we use this I. If I write down that stress, okay, remember this is a sigma x equals mz y divided by I. Now this y equals 1/2 of d, so the mz. Okay, this is d divided by 2, and this is pi d this, and 64. So this leads to mz pi d cubic, and then 32. And this sometimes people call W, and that is named as section modulus. All right, flip this over. So it equals 32 mz divided by pi d cubic. Okay. We can also do a little bit of discussion about the signs. Okay, x is the x-axis, which is the direction of the stress for this case. And S here, we can name S on the surface, and B as the bending stress. So we can name this stress. I just come to this red dot point. I can draw this stress state. Okay, we just pick up a square element and moving out. This is the stress in the x direction. You can call sigma x, you can call sigma b, or even you can call sigma b on surface of b, SB or BS whatsoever, or just simply a sigma. All right, so we draw the stress state for that red point. As long as we define the value of this stress, which is okay, you can use any sign. All right, sign is just a name. Okay, so this is the pure bending case. We can now move to the next, which is an example. I want to talk about the transverse bending case. As you can see from this diagram, transverse bending means that bending is caused by a force applied onto this shaft or beam. All right. All right, for this case, I have here a force applied at this A cross-section upward. And C and D are two bearings. Basically, they do the same thing for this case. Okay, they just provide a normal support to the shaft. And total length of the shaft is L, and A cross-section separates the shaft into two portions, each 1/2 of L. Now we can solve the reaction forces at C and D. Okay, basically they're just opposite and equal in value, which is this F, just 1/2 to this side, 1/2 to the other side. So now we have the free body diagram of this shaft. Okay, the first thing we do is to do diagrams, shear force and bending moment diagrams. Shear force, very easy. This side, based on our sign convention, negative. And this side, based on our sign convention, positive. And in each segment, we just have constant values. They're just two different constant values. Okay? And here, of course, the values are the same, but the signs are different. All right, so now we know that we can plot the bending moment diagrams very easily, because this side, negative slope, and this side, positive slope. That's it. Okay, we can do this diagram very easily. We don't have to play with complicated equation writing. All right, so in the middle, we need to mark the maximum value, which is the force divided by this distance. Force, 1/2 of L, distance, no, force, 1/2 of F, distance, 1/2 of L. So that's why we get this FL divided by 4 as the value of this maximum location. Okay? Right. At this situation, we see that each cross-section, we see different bending moments. Only at this cross-section A, the bending moment value reaches the maximum. Okay? So then we can pull out this point A, okay, and show the stress. And A is under tension, all right? So, and a value of A, of course, is something like this. And stress is along the x direction. Okay, so that is the 32 by moment. Moment is 1/2 of L by 1/2 of F, and then divided by pi d cubic, as what we discussed just before. All right, this is the total expression of the moment for this case. One thing that we need to pay attention, okay, the difference between this one and the pure bending case is that the bending is caused by this transverse force. And this transverse force not only causes normal stress, it also causes shear stress. So we need to look at the transverse shear stress due to the shear force. Okay, we just take this ED segment as the example. We move this out, okay? All right, we move this out because the shear forces are positive for this based on our sign convention. And in each cross section, we should see the same shear force distribution or the same shear force. All right, so again, several conditions. For this case, the surface has to be free of any stress. Okay, so stress has to be in the surface or just in the plane. in the cross-section. And second, integration of the shear stress should come out the shear force. All right? So in order to do our distributions to meet those conditions, first across the section, any cross-section, we should see distribution in value, okay? On the surface, it has to shrink into very small, to 0. In the middle, which is our middle neutral plane, the shear stress reaches the maximum. In the cross-section, which basically is, I flip this over to here, all right? The shear stress is the maximum in the neutral axis. I want to do this here, all right? So this is the cross-section that I'm showing over there. This is the neutral axis, all right? So along the neutral axis, the shear stress has to be maximum, all right? Going upward, it reduces, all right? So middle, still the same thing like this. But on across to the edges, it has to be parallel to the surface. So that's why it is in the surface, not on the surface. So shrink, okay, shrink, shrink, shrink. You keep doing the same thing, like this. Okay, same thing like this. At the top, it shrinks to 0. Bottom, same thing, shrinks to 0. Okay, so this value distribution meet this cross-section we show over here. All right, so what to our interest is the largest value that is along the neutral axis. All right, so maximum shear stress is along the neutral axis. Okay, is along the neutral axis. All right, and how large? That is the shear stress. I use tau, and V means due to shear force V. All right, 4 shear force divided by 3 by cross-sectional area, which we can write simply as this. Shear stress equals 4 4V divided by 3A. Okay? All right. So for this particular case, and we know the shear force is F divided by 2, and all end up with just this total value. Okay. Now, I have a question. How about the shear stress state at 2 points, 1 and 2? Where are 1 and 2? This is 1 and 2. At 1, do we have shear force? Do we have shear stress? No, we don't. So the stress state for 1 is this. It is only the normal stress, which is this one. Okay, we only have normal stress at point 1. 2, at 2, do we have normal stress? Do we have a normal bending stress? No, we don't. So we only have the shear stress. So at 2, this is the case. So at 2, at point 2, okay, we only have this shear stress. So we have to be very clear. These are 2 different things. So even at the same cross-section, at different points, we have different results. We are interested in point 1 because at point 1, we have the maximum bending normal stress. We are also interested at point 2 because at the point 2, we have a maximum transverse shear stress. Okay, so 2 different things. Okay, this is the end for the second part.